Time we're discussing Taylor series. Let's see if this thing is recording. Yes, it is. Great. So last time we saw it here. Suppose that f of x. Oh, sorry. For x, let's x minus a is strictly less than y. Okay, for some r positive. Then what can I say about the derivatives of f at a? Then f, let's say n of a, what is it equal to? Well, then fk of a, let's say, it's equal to k factorial times ck, right? We saw this last time, didn't we? Is that right? Yeah? That's what we saw last time. Great. And what's another thing that we have seen? We could differentiate and integrate it on the interval, what I say, it's a minus r, right? And a plus r. Okay? That's what we have seen last time. Now I'll give you a nice question that you know. That's the use of these series. How to evaluate. Let me check that you can read here. Yeah, okay. Can be read. Let's give an example. Okay, you remember this? Is there any mistake here? Is there everything's good? Yeah? Yes, sir.
Is this on a minus or a times or?
A plus. Plus. Right? Solve this equation, what do you get? Right? Solve this equation. Okay? So far so good? Everybody? Great. So let's give an example of this application. It's a bit harder. Okay, show that for all x in minus 1. What is it that you have? Some x squared. Hope I didn't mess this up. 1 plus x over 1 minus x. Is that it? Let's double check. Times x, I think. Yeah. Okay? I mean, you can check if I made a mistake. But how to start here? What is the big series that you have? I mean, it's difficult, right? A priori, this is not easy to do. Right? How to start? What is the series that you know already? A very nice series on minus 1, 1. The best series that you know on minus 1, 1, the very first series, the geometric series. So what do we have? We have that sum n is equal to 0 plus infinity x to the n is 1 over 1 So I get this formula. How do I get an n squared? You wanna differentiate something to get an n squared. How can you do that? So what if I multiply by x on both sides, and then I differentiate? If you multiply on x by both multiply by x, each side you multiply it by x. What do you get? You get nx to the n. The series of that is equal to x over 1 minus x squared. Isn't that right? And then what do? You have nx to the n. How do you get n squared x to the n? You differentiate, right? The n squared, x to the n minus 1, and then you multiply by x. Okay? Let's do this. Multiply by x on both sides, hence sum n equal 1 to infinity n x to the n. Great. What do I do now? How do you get an n squared here? Well, multiplying by n is the index, so it's a bit difficult to multiply by n. N is varied, right? Now how do I bring this n down? What operations allow me to bring this n down? Differentiation, right? So n equal 1, so this is n equal 1 to infinity, n squared x to the n minus 1. Differentiate this one. What do you get? U prime v. U prime is 1. V is here. Minus v prime u, right? Well, plus 2. 1 minus x over u squared. Let me write this one here. So I get sum n equal 1 plus infinity n squared x to the n minus 1. What is that equal to? Cancel out 1 minus x. So you get 1 minus x plus 2x. So you get 1 plus x over 1 minus x cubed. And how do you get here? What do you multiply by? X. Hence. Okay? It's not easy, but you can, you will get the habit. Okay? Is it clear? Is it clear or not? It's not easy. But what is the idea? Is multiplying by x and differentiating. This is the whole thing you gotta do. Multiply by x and differentiate. Okay? And this kind of thing. Okay, so this is a bit the use of these things. So for example, if I tell you what's the sum of n squared divided by 2 to the n, the series of that, you can just plug in here. Right? Yes, sir.
So what happens to the index in that step where you differentiated first?
Sure. What's the n equals 0 term?
0.
No, x to the 0 is 1.
Yeah.
Okay? When you differentiate it, you ignore it.
Right. So it cancels out.
Exactly.
So why didn't you do that in the second differentiation?
Where?
In the second one here.
Here? Where?
This one.
Sum n equal 1? Yeah. I differentiated. So what is the first term here?
Yeah. Yeah, you drop the n down and you get n squared.
No, but what is the first term here? It's x.
Right.
Right?
Yeah.
Differentiate x, what do you get?
1.
What's the first term here?
Oh.
Okay? Okay, is that good?
Yes.
I mean, the idea is that you don't want an x to the negative 1. If this is right.
Right. Yeah.
Okay? I mean, n equals 0 times x to the negative 1, this is 0. Okay? But
I'm just not sure why. Okay. I'm just not sure why we changed the index there. I understand what you're saying, but I don't like.
Sure.
Why
Do
did
you
that
agree,
work?
do you nice application of this. Any questions on this? Any questions? Great. Let's do one more. Well, another question. Who volunteers to give me a number? An integer? Positive integer?
3.
Something a bit bigger?
13.
13. Great. Fine. The 13 derivative at 1, see what I have. In f of x, definitely, one way to do it is to differentiate 13 times. But that's definitely not the most efficient way. How to do this? We can use power series, right? Around what number? What is my a here? X minus a should be a. So what does the theorem tell me? It tells me that if I have a power series, then the k derivative at a is equal to k factorial times the coefficient of x minus a to the k, right? What is my a here? It's 1. So I need to express this in terms of x minus 1, powers of x minus 1. Isn't that right? Right? So I have to write this of this form. X minus 1. Right? If I'm able to do that, then I could find the 13 derivative of f at 1 by looking at what is the coefficient of x minus 1 to the 13 and multiply it by 13 factorial. Right? Yes? Are we good here or not? Yes? Great, so how do I do this? So first of all, I want to write this thing, I want to write 2 plus x, I gotta let an x minus 1 appear here, right? The idea is that I want to let an x minus 1 appear and use the geometric series formula. You see that? 1 over 1 minus x. You can use the geometric series formula. Why don't I use it here, but instead of x I have x minus 1? Right? Now, is this equality true? Is this equality, this thing I wrote, is it true? Is 1 over 2 plus x equal 1 over x minus 1? No. What do I need to add? I need to add 3. Okay. Now again, let us remember what is the geometric series formula. This is 1 over, let's say, 1 minus a, an, if absolute value of a is strictly less than 1. So I gotta make this 3 equal to 1. How do we do this? Yes? Let me factorize by 3, thank you. I factor 3 out. Now that's nice. I can apply the geometric series. Perhaps if I put a minus minus, right? I can apply the geometric series formula. Do you agree or not? Let me write this way. So it's 1 over 3 times 1 over 1 minus x minus 1 over 3. Now I can apply the geometric series formulas in x minus 1 over 3. 3 to the n plus 1. Did I have it right? Yeah, x minus 1 to the. What is f13 at 1? The 13th derivative of f at 1. What coefficient are you looking for of x minus 1 to the 13 and multiplying it by 13 factorial, right? So f13 of 1, so it's minus 1 to the 13 times 3 to the 14 times 13 factorial. Is that cool? Is that good? Yeah, have you seen this in Calc 1, Calc 2, Calc 2? No? Okay. Nobody has seen this, even if when you took it like the fall? No? Okay. Anyways, we'll get better at this. Definitely homework will definitely help. Okay. Very good. Is it clear? Should we do more examples like that, or let's do one more? I'll take one from the book, I guess. Let me pick one from the book and see. Okay. Someone give me a number. Who volunteers to give me a number? An integer? 12. Okay, is that good? Let's do that. Find f12, let's say of 2, if f of x is equal to log x.
Would you put that in the form of len 1 plus bracket x minus 1? And that way,
X minus 2.
oh,
X of 2.
sorry.
Yeah. Very good. So what is f of x? F of x is ln x, which is just ln of 2 plus x minus 2. Right? Agreed? Now, remember there is something that I have. I have the formula of ln 1 plus t, or what did we do? Ln 1 minus t. Is that what we did last time? Ln 1 minus. Okay? We have this expansion of this one. Now since I don't remember it by heart, how do we get this one here? How do we do it? We start with the geometric series, and what do we do to both sides? We integrate both sides. We have a constant, and then we have to find the constant. How to find the constant? We plug in a value, right? Should I do it, or so let's see. Let me redo that. So you integrate x to the n, right? You integrate that. This is 1 over 1 minus x. Integrate that. On this side you get minus ln 1 minus x is equal to sum n equals 0 plus infinity x to the n plus 1 over n plus 1 plus c. Right? You remember this? You guys remember this? We did this last time. We integrated both sides. So you put the minus there. You get here. And you plug in c equals 0. You get ln of 1 is equal to 0. Sorry, you plug in x equals 0. You get ln of 1. Is that the expression we got? Is that the expression we got last time? Yes or no? Yeah. Or we wrote it this way, sum n equal 1 to infinity that a problem or not? How can you deal with this term? The long 2, the 2 is annoying, right? 2 is annoying. Because you cannot really apply your formula, but there's something easy that you can do if we remember our ln properties. Yes? We can split it up. Exactly. So ln A times B, what is that equal to? It's ln A plus ln B. So I have my ln 2 here plus ln 1 plus x minus 2 over 2. Agreed? So far so good? Now can I apply this? If I do the minus shift, if I write it as minus minus? Yeah. Very good. Ln 2 plus ln 1 minus what? Okay. I need to put brackets here. So this is just ln 2 plus sum n equal 1 to plus infinity. What do I have? I have a minus. Then I have a minus x minus 2 over 2 to the n. Then I divide by n. And that's it, right? I mean, I can do that. I can simplify it. Sum n equal 1 to plus infinity. What it does, this becomes minus 1 to the n plus 1 over n times x minus 2 to the n. I have here a 2 to the n. Great. So what is f13 at 2? What is the third derivative of f at 2? What do I need to look at? I need to look at the coefficient of x minus 2 to the 13 and multiply this coefficient by, I need to x minus 2 to the 12, sorry, and multiply this coefficient by 12 factorial. Right? Great. So what is the coefficient of f to the 12? So f to the 12 at 2. This is just, so what is the coefficient of x to the 12 here? For what value of n you get x minus 2 to the 12? N equal 12, right? So 2, so you get minus 1 to the 12 plus 1 over 12 times 2 to the 12 times 12 factorial. Okay, then you can simplify, so you get minus 1 to the 13 is just minus 1. Minus 1, 12 factorial divided by 12 is just minus 11 factorial divided by 2 to the 2. Okay? Is that clear? Is that good? Try to find a nicer example, but let's see if there are nicer examples. But yeah, okay. Yes.
For the x minus 2 to the power of n, x takes the value of 2.
X?
Does x take the value of 2?
No, when you're looking at, so x does not take the value, well, it could take the value, let me just say something here. X minus 2 divided by 2 is less than, very important, less than 1. Okay, I forgot this one. What is it?
I mean, the thing is that x takes the value of 12.
Yes.
Okay, so you just.
You just extract the coefficient, okay? what's the coefficient of x minus 2? It's minus 1 squared over 1 times 2. Right? This is your C0, basically. Okay? Yes, sir.
Why do you use the negative one and then add to the plus one, not just the same one at the end?
Where?
In the bottom line.
Here?
Yeah.
You have a negative 1 to the n here,
Yeah.
times negative 1,
Okay.
negative 1 to the n plus 1. Okay? You're asking if you can put minus 1 and minus 1?
No, I just wonder why.
Oh, okay. Negative 1 to the n here times negative 1, negative 1 to the n plus 1. Is that clear?
Yeah.
Yes, sir. Why do I simplify where? Here? No, it doesn't. I'm able to read the coefficient in a nicer way. Exactly. Times x minus a to the n times the coefficient. Exactly. Exactly. So you want this part. Times k factorial. Okay? Yes, sir. If you memorize it correctly, okay, that's an important question. If you memorize it correctly, then you know you could use it. Definitely. So you can use it if you have it, but if it's wrong, you're in trouble. Okay? So I personally prefer that you read it right.
I can just do this, like, if I memorize it correctly.
Yeah, yeah. Yes, sir.
How many forms like this do we need to know?
Like, so you don't need to know any of them by heart. Okay? How many of these forms can you use without rederiving them? About 10, basically. 10, 8, something like that. Okay? Yes, sir.
On the first line in section 4,
Yes.
why do you return the positive and negative substitution so
Oh, because I have ln 1 minus t here, right? I just want to plug t equal minus x minus 2 over t. Okay, is that clear? I mean, what you could have done, you could just put a 2 minus x here, but it's not nice. Okay? It's not very nice. Any question? Yes, sir. The value? Here? If you put a 2 here? T? No, let's say you put t equal to, what do you get? Exactly. This is the interval of convergence. Right? If t is bigger than 1, it doesn't work, right? Plug in t equal 2. And does it make sense? Ln 1 minus 2. It's ln minus 1. Right? Okay. Should you do one example? Should you do one more example? Let's see if we can do one more. Yeah, now I'll pick one from the book. There are many ways to do things like that. But let's okay, so I'll try one just on the spot. Okay? Let's pick one on the spot. Find the values. What time is it exactly now? 45? 11:40? Okay. Yeah. Let's see. Okay, let's try one. Second. Okay, find the value does it look easy? Doesn't look easy. Okay, now first of all, let me try to simplify things. Okay, so how do we start usually when you have a problem like that? So usually the n plus 1 comes from a derivative. Right? So n plus 1, like how do you get n plus 1 when you differentiate? You need to have x to the n plus 1, right? When you differentiate x to the n plus 1, what do you get? You get n plus 1 times x to the n. Well, differentiate once more. You get n plus 1 times n times x to the n minus 1. Okay, so we kind of have an idea where to start here. Okay, so let's try this. What's the best series that you know? The geometric series. Let's start with the geometric series. For x, strictly less than 1. Okay, now what you really need to get, you need to get an n plus 1 here, right? The idea is that you want an n plus 1. So what do? I multiply by x on both sides. Very good, thank you. I have to be very consistent with my x notation. Okay, how do you bring the n plus 1 down? I differentiate, right? If you differentiate, what do you get? Very good, awesome, thank you. Oh man, okay, n plus 1 x to the n, yeah. Differentiate the other one. U prime v minus v prime u. 1 times 1 minus x. 1 times 1 minus x. Minus v prime, so it's plus x over 1 minus x squared. So which is just 1 over 1 minus x. What? Yeah, okay, looks good. Yeah. Looks good. Is that good or not? Yeah, it's good. Right? It's good. Yes, sir. Yes, ma'am. No. So you differentiated? No, that's fine. That's fine. What's your first term here? X, right? X plus x squared. X plus x squared plus, right? What's the derivative of x? 1. Plug in n equals 0. Yeah. Yeah.
Sorry, but what did you do to simplify that into the thing on the left?
The thing on the left?
Yeah.
Where? Here?
Yeah, what did you do to simplify that?
Here? From here to here? 1 minus x plus x, what do you get?
Oh, okay.
Okay? Just differentiate. Okay? Great. So now what do? You need an n. What do? Someone else who can volunteer? Who volunteers to give me the next step? Someone else? Yes, sir.
Differentiate again.
I differentiate again. Or maybe differentiate. Differentiate. First step. Then differentiate again. What do you get? Well, right? You differentiate this is what you get. Right? Or no? Are we good? Yes, are we good or no? Yeah? Let's differentiate 1 over 1 minus x squared. So 1 over 1 minus x squared, 1 over u, it's minus u prime over u squared. Or you can write it as 1 minus x to the power minus 2. Right? You differentiate that, so it's minus 2 times minus 1 times 1 minus x to the minus 3, right? Yeah? Are we good? So if you write this 1 minus x to the minus 2, you get minus 2 times the derivative of 1 minus x, which is minus 1, times 1 minus x to the minus 3, which is just 2 over 1 minus x cubed. Is that right? Now, does it look like what I need here? Of course, here is x still less than 1, that's good value. Does it look like what I need? Look at the sum I need. The sum I need has minus 1 to the n over to the n. Is that a problem? I can just combine them together. Isn't that right? I just can write minus 1 over 2 to the n. Maybe this should be the first step actually, to just note this. Right? N times n plus 1 times x to the n. N times n plus 1 times x to the n minus 1. Oh, wait a minute, but is that a problem or not? What can I do here to get here? I multiply by x. Exactly. Let me multiply both sides by x. And then what value do I plug in for x? Sigma n equal 1 to plus infinity n plus 1 x to the n is equal to what? To 2x over 1 minus x cubed. Is that right? Yeah? Yes?
When you differentiate again, why are we starting from n equal 1?
Sure. You can start with n equals 0. Okay? You get 0 times 1 times x to the minus 1. Okay? So I just want to avoid writing x to the minus 1. Okay? But n is 0. Okay? So goes up. So it's 2x over 1 minus x cubed. Okay, now what do you do? How do you find the value of the series that you want? Of course, all of this holds if x is less than 1. So what do you do here? You need the series n times n plus 1 times minus 1 half to the n. So what do you plug in for x? Can you do that? Are these two functions equal? Is this series equal to the function at x equal minus 1 half? Why? Because it's an absolute value, it's less than 1. Very good. Thanks. Less than 1. Is equal to 2 times minus 1 half over 3 halves cubed. What is that? 2, this is minus 1 minus 2 cubed over 3 cubed. Is that right? So you can expect a question like that, for example. This is a fair question, fair multiple choice or long answer. Yes? Okay, so the idea is that I don't want to get, so if you start at 0, right? You get n times n plus 1 times to the x n minus 1. Okay? Plug in n equals 0, what do you get? 0. Okay? Times n plus 1 times x to the minus 1. I just don't want to write x to the minus 1. Okay? But it's still the same. You can still put n equals 0, right? It still doesn't change, does it? Try to put n equals 0, what do you get? Start the first term, what do you get? 0. So why not start with n equal 1? If the first term is 0, why do you want to start with n equal 1? Okay? Are we good? Did I mess up a number or something? Looks good? Okay, so things like that. I don't know if they do these in this course in general, but we did this. So you're responsible for things like that. Okay? Yes? Oh, no question. Any questions? Great. So enough of this stuff. We'll continue with more related stuff now. Taylor and Maclaurin series. Please ask. All good? All good with this stuff? Maybe I can post some practice on this. Okay, I can post some practice. That way you can practice it. And there are some where you have to integrate as well. So I don't don't know any example off my head, but you can, there are some things where you may have to integrate, but let's see. Okay? Okay, great. Now, review, also review, Taylor, and Maclaurin. Oh, by the way, I remember something. I posted my office hour on my courses. Did you guys see them? Okay, you didn't see them. Great. I posted them. I don't know when they are, but I posted them. It's 1 hour and a half, and then there is 1 hour and a half. Instead of formal office hours, I can hold an exercise session. Basically, do examples and then answer all the questions in common. So we sit in a classroom, and then you guys ask me questions. It's, I think, better than because you answer one question for like 5, 6 people at the same time, and which is good. And then I can do examples in the remaining time if if you don't have many questions. Okay? And I think this is more efficient, and it has worked well. So I taught a course in fall 2024. I did this. The grades were very, very good. Usually, and many people said because it was, you had a lot of exercise sessions. So let's try it again. I mean, it's a different course now. Let's hope it works. I think in this course it should work better actually, but let's see. Let's hope so. Great. So Taylor and Maclaurin series, and I gave a survey, right? Please fill the survey in. Okay, there is a survey in my courses for your favorite time. Please fill it. I'll try to record the sessions as well. Okay. Now there's a problem is that my course is not giving notifications. I don't know why, but that's okay. You can just have to check every day and see if there's anything. I don't know. I've had that problem. I'll try to fix it. But anyways. Okay, so motivation. So let's recap the motivation. Okay, guys, everybody, let's do the motivation. What was the motivation behind Taylor and Maclaurin series in Calc 2? The motivation really, there are many ways to motivate this. I mean, we can, with what we have seen right now, we have seen that if f of x is of this form, for x minus a is less than r, where r is positive, then we can say that fn of a is equal to n factorial times cn, or that cn, equivalently that cn is fn of a over n factorial. Now, if f is differentiable, if f is infinitely differentiable at a, if f is infinitely differentiable at a, can we write f of x so suppose f is infinitely differentiable. Can we write this series? Can we always write this? We have seen this for series like 1 over 1 minus x, right? If a is 0, we can write this series provided that the interval is minus 1, 1, right? We wrote it in terms of the series of x to the n. Now, if I give infinitely differentiable at a, can you always write this? This is a question that we'll answer. This is a motivation for that. Now, a second motivation, if you try to look at the first few terms of this one, what is the first term here? What is the first term? C1, what is C0, sorry? C0 is what? C0 is just f of a, right? So if f of x I'll just replace Cn by value. What is C0? This is just f of a. What is the second term? N equal 1, what do you get? F prime of a divided by 1 factorial times x minus a, right? And so on. Write this expansion. This is what you get. Isn't that right? C0 is f of a. C1 is f prime of a. C2 is f double prime of a over 2 factorial, right? Now, what is this? What is the first term? Does this remind you of something? What does this remind you of? Calculus 1. What does it get her?
Linearization.
The linearization, right? This is the tangent line approximation. Do you remember this or not? You remember? This is the tangent line approximation. What do you use the tangent line approximation for? What did you use it for in differential calculus? What was its use?
Slope of the line.
As the slope of the line, sure, and plus the f of a, but what did you use it for? What was the main use of this? Yes, sir.
Find the derivative at point A.
Sure, I mean, usually you have the derivative, you find it, and then you write the tangent line, right? What's one use of this tangent line business? Yes?
Approximations for derivative.
For derivative or for f of x? Right? So if x is close to a, in differential calculus, if x is close to a, right? You remember this? In differential calculus? No? Math 140. This is the tangent line approximation. Or a linear approximation. Remember this from math 140, or what is it, the other one? 139? You did this, no? 100% sure you did it. Yeah? This is a tangent line approximation. Now, what is the degree of x minus a? To what degree does it go? To what degree? It's a linear. So what is the degree of this? 1. Now, can you perhaps do better than this? Can you do better than the degree 1? The answer is that you may be able to, by considering terms of higher degree. What is the term of higher degree that you would consider here? The prime of a over 2 factorial times x minus a squared. Okay? This is really the motivation. So you have two motivations. You have one, power series related. So if you can express f as a power series, then you can read off the derivative of f at that particular point by looking at the coefficient of the series. Another motivation is the tangent line approximation. how do you approximate f of x? When x is near a. In Calc 1 you have seen that I draw the tangent line, and I approximate f of x by the tangent line, right? If x is near a. You have seen this, no? Now, what if you want to increase the degree? The tangent line has degree 1. It's a function of degree 1, a polynomial of degree 1. This has polynomial of degree 2. So really, if you approximate f of x, you may be able to approximate it with this. F of a plus f prime of a times x minus a plus f double prime of a times x minus a squared if x is near a. Let's draw a small picture. And let's draw the curve y is equal to the x. What's the tangent line at 0? Tangent line at 0 of y equal to the x is y equal 1 plus x, right? This is the tangent line at 0, right? Differentiate e to the x, you get e to the x. F prime of 0 is e to the 0, which is 1, right? So it's y is equal f prime of 0 times x plus f of 0, which is just e of 0 is 1, e of 0 is 1, which is just x plus 1. Right? This is the tangent line approximation to y equal e to the x. Now let's look at a degree 2 approximation using some sort of power series. I have f prime of, I have f of 0 plus f prime of 0x plus f double prime of 0 to 2 factorial divided by 2 factorial x squared. F double prime of 0 is also 1, right? Because if you differentiate e to the x, it never changes. This is 1 plus x plus x squared over 2. I gotta be careful how I'm showing this. Like that. Oh geez, okay. I think it should be something like this. Well, I don't know if you've seen it, but y what is a better approximation? 1 plus x or 1 plus x plus x squared over 2? What looks like a better approximation? The parabola lies between the line and the curve I'm approximating. Isn't that right? You see that? So what is a better approximation? The parabola is a better approximation, right? And it's sort of tangent to the curve, right? You see that? Try to draw it in a better way. You see that it's sort of tangent to the curve. Basically, what is the tangent line of the parabola at x equals 0? It's the same tangent line to the curve. Right? You see that? So the parabola here, the tangent line, this line is tangent to both the parabola and the curve. That's nice. Right? So technically, you may be able to assume that with this parabola, which has the same tangent line, the linear approximation of e to the x and 1 plus x squared over 2 is the same if x is close to 0. Okay? This is really the motivation behind this. Great. Okay, is it clear? Any questions on this? Sorry if it's a bit fast, but again, I'm a bit behind schedule, so I'll have to go a bit faster. Again, this was supposed to be seen in 141, but we just explained a bit faster. But really, this is the motivation. The motivation, instead of linear approximation, I could do a quadratic approximation. You could do a cubic approximation. You could do a degree 4 approximation. This is the idea behind it. Okay? Great. Definition. Let f be infinitely differentiable on an interval, say a minus r, a plus r, for some are positive. The Taylor and polynomial of f of x around x equals a, or around a, is, I'll call it p or t n of x. It's the sum of k equals 0 to n, f k of 0 over k factorial times x minus a to the k. Let's do a small example. I have k of 8, sorry, it's not 0 here. It's 8. It's around 8. Okay, find T4 of x around a equals 0. If f of x is cosine x. What is this really? This is just f of a plus f prime of a times x minus a plus dot 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 f k of a times k factorial, sorry, f n of a times x minus a to the n. So let's find T4 of x if f of x is equal to cosine x. How can I do this? What do I need? So what is T4 of x? Let's write this. It's f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 divided by 2 factorial times x minus 0 squared. I mean, let me just write it here. See here? Plus f triple prime of 0 is 3 factorial x minus 0 cubed. Okay, f of x is equal to what? To cos x. What is f of 0? What is f of 0? 1. What is f prime of x? F prime of x is minus sine x, right? If fx is cos x, f prime of x is minus, let's write this. F of x is cos x. F prime of x is minus sine x. F prime of 0, what is it equal to? What is it equal to? F prime of 0, what is it? 0, right? So this is 1 plus 0 times x minus 0. F double prime of x minus sine. What's f double prime? It's minus cosine. Okay, minus sine minus cosine at 0, what is that equal to? Negative 1/2, very good. So it's negative 1 over 2. The 1/2 comes from here. What is f triple prime at 0? So f triple prime is minus cos x prime, which is sine x. Sine x at 0 is 0. So this is T4 of x, the T3 of x. Oh, here I have T3. Sorry about that. In physics, you've seen the approximations that cos x, if x is small, is 1 minus x squared over 2, right? Have you used this before? That if x is small, then cos x approximation you have seen. Sine x is close to x. This is just the tangent line approximation. Right? Sine x is close to x is just the tangent line approximation if x is small. Write down the tangent line of sine x around x equals 0. You just get y equals x. Now here, what does the tangent line approximation give me? If I were to stop at the tangent line, what would it give me? What would the tangent line approximation give me? Stop at degree 1, what would it give you? It would give you 1. Is that a good approximation? I'm saying if x is close to 0, then cos x is close to 1. Great, sure. Is that a good approximation? Is it a good, or can you do better? What is better? 1 minus x squared over 2? Or just 1? What is better? 1 minus x squared over 2, right? This is the use. What is an easier approximation is 1, right? But it's less accurate, of course. Okay? Should you do one more or not? We do an example like that. So who volunteers for a nice function? Let's see. Who wants to volunteer for a nice function? Or let's try to do an order k approximation. If f of x is cos x. Find d n of x, say. Should you do cos or should you change a bit? Change to sine or cos to sine? Cos is fine?
No.
Sine? Put sine. Sine x around a is equal to 0. Okay, let's do this. What do I need? I need as many n derivatives. So I have f of x is sine x. So what is Tn of x? Tn of x is just the sum from k equals 0 to n. Sk is 0 over k factorial times x to the k. Right? I just replaced a by 0 quickly. Are we good here, folks? Everybody? Great. Well, f of 0, what is f of 0? So f of x is sine x. What is f of 0? F of 0 is 0. Okay, what is f prime of x? Sine, derivative of sine is? Derivative of sine is? Cosine. So what is f prime of 0? F prime of 0 is 1. Now what is f double prime of x? F double prime of x is minus sine. So what's f double prime of 0? F double prime is right here. F double prime. Okay, now what's f triple prime of 0? Minus cosine. Very good. F3 of x, sorry, is minus cosine. What is f? This is f2 here. This is 2 derivatives. This is 3 derivatives. Minus cosine of 0, what do you get? Minus 1. Okay, what is the fourth derivative of cosine? What is the fourth derivative of f? So what's the derivative of minus cosine? Sine. So f4 of x is sine x. What happens now? What happens? I have a cycle, right? So what's the eighth derivative of sine x? Sine x. What's the fifth? What's the, let's see. What's the third? Well, what's the sixth derivative of sine x? What is it? Minus sine x, right? Okay? Are we good? 4, 5, 6. Right? 7, 8. Okay, so if n is odd, what is fn of 0? If n is odd, sorry, if n is even, say. Let's start with the even case. If n is even, what is fn of 0? 0, right? 0, 0, 0. Here is not 0, here is 0, right? You see that? Okay, fn is 0 is equal to 0. Does that make sense or not, by the way? Does that make sense? Sine is an odd function, right? Sine x is an odd function. Right? You see that? If n is odd, what is fn of 0? Okay, so if n is odd, it's a bit harder. Okay, but I still can do better. Can I find a nice formula for it? Yes? Minus? Let's check that. What is f prime of 0? What is f3 of 0? It's minus 1. So, let me do it this way. This may be easier. What is this? What's this? This is easier, right? 2n plus 1 is an odd term. Okay, this is easier. What's this? Plug in n equals 0, what do you get? If n is equal to 0, what do you get? If n is equal to 0, you get 1. If n is equal to 1, what do you get? If n is equal to 1, you get f triple prime, which is negative 1. If n is equal to 2, what do you get? You get f5 of x, the fifth derivative of 0. What is it, the fifth derivative of 0? 1. So here, what is it? Minus 1 to the? Try it. If n is equal to 0, what do you get? Let's say it's minus 1 to the n minus 1. Okay? If n is equal to 0, you get f prime of 0. Right? What is f prime of 0? Well, let's do n plus 1. What's f prime of 0 is 1. What is minus 1 to the n plus 1? This is minus 1. Does it work? Does this work? If n is equal to 0, what is f prime of 0? 1. Minus 1 to the 0 is 1. Okay, if n is equal to 1 here, you get f triple prime at 0. N is equal to 1, it's minus 1. Okay? So what's the Taylor nth polynomial? This is going to be a bit hard. Of sine x. What is it? This is a bit tough. It's not easy. Yes? Well, sure, but this may depend if n is odd or even, right? Right? You need a degree n at most. You see that? Yes? Sure, I mean, but I want the polynomial of degree of the largest power of x is n. Right? Let's do an example. If the largest power, if I want p5 of x, what is that equal to? T5 of x. Let's do that. This is just f of 0 plus f prime of 0 x. Okay. Every even derivative will cancel. So f of 0 is 0. This is 0. f5 is minus 1 to the 2, right? You see that? Plug in n equal 2 here, you get f5 of 0. So what do you get? You get x minus x cubed over 6 plus x5 over 120. Right? You agree? Now, if I tell you what's the degree 6 polynomial, what's T6 in that case? T6, no, T6 is the whole thing. It's the whole thing. What is T6? It's the same, right? Because at 6, the sixth derivative at 0 is also 0, right? So T5 is equal to T6. Okay, so Tn of x depends on whether n is even or n is odd. Yes, sir. Where? Minus x, right? Okay? So really, Tn of x depends on whether n is odd or n is even. Okay? Are you good here? Are we good? Is it clear? So, okay? So I'll let you write it in the next way. I'll let you find a general formula, although it's useless because we'll use a better formula. Well, find a general formula for n, if n is odd or n is even. Okay? Doesn't matter, it's not a very nice exercise. But the most important is that you'll be able to do this. If I tell you find the degree 7 polynomial, the Taylor 7 polynomial of sine of x, what do you get here? It's minus x to the 7 over 7 factorial, right? You just add this. If I tell you find T8, what is T8? It's equal to T7. Agreed? Is it clear? Are we good here? We do one more like that? Should we do one more? Let's do for cosine. I mean cosine, well, let's read it. Okay, is it clear or not? Is it clear? Yeah? How to find a Taylor polynomial of degree, the Taylor 10th polynomial? You just have to take 10 derivatives. Okay? Now sometimes you may find a pattern like this case. Yes?
How is your access to sigma notation?
In sigma notation. So which one do you want? T6? Okay, sure. Let's try T5 in sigma notation. Very good, okay. So you're summing only odd terms. That's a very good question. I was going to do it later, but since you asked, let's do it now. T5 of x minus x cubed over 6 plus x to the 5, right? So you're just summing odd terms. Odd powers, basically. Let's write it this way. N equals 0. Let's say f 2n plus 1. So 1, 2, 3. So n is equal to 2. X 2n plus 1. Right? If n is equal to 0, 2n plus 1 is equal to 1. If n is equal to 1, 3. If n is equal to 2, 5. Great. So now you've dealt with this. Okay? Now, what is the factorial that appears here? This is the same as 2n plus 1 factorial. Right? Now, what is the coefficient that appears here? do one more? One more, or is it good? I think it's good. Okay, just have to take derivatives. Sorry if it's a bit fast, but we should now move on. Okay? Yes? Where the T5 for 2, okay. So you agree this is the polynomial, right? Okay, you want to write in a nice summation. Notice that the odd powers of x are appearing, right? And any odd number, you can write it as the form 2n plus 1. You agree? So, start with n equals 0. Which power do you recover? First one. Start with then n equal 1. Which power do you recover? What power do you recover? Okay? Is that clear? So if you wanna do T8, will you be able to get a degree 8 polynomial in that case? No. Where will it stop? 7. Okay? Very good. So for T8, or let's say here you have T5, T6 will also be equal to T5 in that case. You see that? Because T6, what's the next term that's coming? X to the 6. Guys, what's next term? 0, right? 0 x to the 6. So T6 will be equal to T5 in that case. T7 will be equal to T8. You see that? Here, what are the derivative of n to the 7th? What are the derivative of f of x? The 7th, what are the derivative of e to the x? Exactly. Depends on the function. Okay? The derivative of e to the x at 7 are just e to the 7th. All of them. So it's never 0. Here, why were you able to cancel the x squared? Because f double prime of 0, I had it written there, is 0. F of 0 is 0. Right? Is that clear? Okay. Any questions? Are we good? Great. Now let's move on. Lagrange's remainder. Have you seen this in Calculus 1? Lagrange's remainder? You may or may have not seen it. Have you seen the mean value theorem or not? Okay, very good. This is just the mean value theorem in a more advanced form. Okay, I'll simplify the assumption. The assumptions can be more relaxed, but I'll just simplify. Let f be infinity. Okay, this can be dropped. Differentiable on a minus r, a plus r, for some r positive. Let Tn of x is equals be the Taylor and polynomial of f of x above x equals a. Okay? So the derivative, Tn is the generalization of the tangent line approximation. Do you agree? Tn is a generalization, T1 is a tangent line approximation. Tn is just an approximation of order n. I don't want to say degree n because Tn may have degree less than n. But, so Tn be a Taylor n polynomial f of x about x equals a. Now what's the thing? Then, f of x is equal to Tnx plus, what they call it r, plus Rnx, where Rnx is what? it's not easy.
Inclusive, exclusive.
Exclusive, exclusive, I think, is more safe. Differentiability is always on open. I mean, if f is constant, for example, you know, right? So I usually use the exclusive. I think. Yeah, because differentiability is always on open interval. Well, it could be inclusive as well. For example, as long as it doesn't contain a minus r a plus r. Okay, great. Now, does this remind you of something? Does this remind you of the mean value theorem or not? So take n is equal to 0. Okay? F of x, right? Mean value theorem. What does it say? It says f is infinitely differentiable. Let's assume it's infinitely differentiable. F of x, what is the degree 0 polynomial? Taylor's 0 polynomial, just f of a, right? So f of x minus f of a is equal to f prime, if n is 0, right? F prime of c times x minus a. If n is equal to 0, we recover the mean value theorem. This is just a generalization of the mean value theorem. And you prove it by induction. Okay? You don't need to know how to prove it, but. Right? What is the Taylor 0 polynomial? This is f of a, right? You've seen this? T0 is just f of a. F of x minus f of a is just f prime of c for some c between a and x times x minus a. Do you remember this mean value theorem? Or no? Did you remember this here? F of x minus f of a is just f prime of c times x minus a. Yes or no? You remember this? Okay, this is just a generalization of it. Instead of working with the Taylor 0 polynomial, which is f of a, I work with the Taylor n polynomial. And I have an n plus 1 factor. Okay? The proof is by induction. You have seen that or you have not seen that, I don't know. You could, or it's possible, both are possible. But this is it. Now, if this term goes to 0, what can I say about Tn? Does my Tn approximate my fx well? If this remainder is close to 0 and then is large? Suppose that this remainder shrinks, goes to 0. Can I approximate f of x by Tn? This is the whole point. Okay? Yes or no? You see that? So the idea is that for what are the conditions on f so that Rnx goes to 0? Okay, this is a very important theorem. Okay, can I write this? Is it clear or not? Is this clear? So f of x is Tn x plus Rn of x, where Rn, there's an integral form for it. Do you want me to write the integral form? I don't think it's important. Have you seen the mean value theorem for integrals? No? Doesn't matter. Anyways, there's another form for it, but let's not worry about it. Okay, let's stick with this form. This is called the Lagrange remainder. Okay, so if you take n equals 0, you recover the mean value theorem. Anyways, it's nice. But let's suppose I'll rewrite this. Another theorem. Well, I don't want to write it here, just to double check if it's good. I'm going to write here. suppose that f is infinitely differentiable, and that f of x is Tn of x is Rn of x, where Tn. Okay. If the limit and then goes to 0 to Rn of x is equal to 0, absolute value equal, or x minus a is less than r, then f of x is equal to some. So, if you have the remainder, the Rn of x that goes to 0 as n goes to infinity here. If n goes to infinity, then f of x is actually equal to its Taylor series. So if I give you sine x, what is the Taylor 7 polynomial? What is the Taylor fifth polynomial? It's x minus x cubed over 6 plus x5 over 120, right? Now you can keep on going. So you get x minus x cubed over 3 factorial, plus x cubed over 5 factorial, minus x7 over 7 factorial, plus x9 over 9 factorial, and you can keep on going. Now, provided this remainder goes to 0, then you can represent sine x as a power series. Okay, so you will not be questioned directly on this theorem. This theorem is like, I think, beyond the scope of this course. You just have to know that if the remainder goes to 0, then you can write your function as a power series. This is what you have to know. Okay? Let's do this. Let's give an example. F of x is sine x. Yes, sir.
And so this is true for any a that's chosen as long as it satisfies that inequality.
What do you mean? So you fix A first. A is fixed.
Okay.
Okay? Once you fix A, if f is differentiable on a minus ra plus r, then and limit Rn of x is 0, then that's what you get.
But you can choose any a. The choice of a is r.
Provided, yeah, exactly.
Provided this.
Yeah, I mean f has to be defined as a and infinitely differentiable.
Sure.
Okay. Should we do an example or not?
Yes.
Let's do an example. Let's do an easy example. Okay, what is the Taylor polynomial of sine x? If you want to add them up together. So what we have seen, how to show that sine x is equal to sum of n equals 0 plus infinity minus 1 to the n I mean, here the indices don't really matter, okay, because if you stop at even n, it's, anyways, right, notice that if you wanna stop at x5 and you stop at x6, it's the same for unit, okay, so we'll just consider for odd n, where sorry if I'm going fast. Some let's say k equals 0 to n minus 1 to the n x to the 2k plus 1 over 2k plus 1 factorial. Now what is Rn1 plus of x is equal to f the 2n plus 1 of c divided by 2n plus 1 factorial times x minus, sorry, times x to the 2n plus 1. Is it 2n plus 1? No, I don't think it's 2n plus 3.
Doesn't matter.
Right? Let's see. So fn. That's a difficult one. So let's see. Oh man. So you stop at 2n plus 1. So that's 7. I think no. I think it's 2n plus 2. Yeah. Right? It's 1 degree more than the last derivative. So what do you get? Does Rn go to 0 or not? Does Rn go to 0? Whatever this is. Okay. Now, the derivative of sine, all of them are either cos or minus cos or sine or minus sine, right? In absolute value, what are they? They're less or equal to 1. So this is less or equal than x to the 2n plus 2 over 2n plus 2 factorial. What is this limit? What is the limit of x to the 2n plus 2 divided by 2n plus 2 factorial? It is 0. Right? Do you see that? Why is it? Why is that? Why is the limit of x to the 2n plus 2 over 2n plus 2 factorial equal to 0 and then moves to infinity? Is it obvious or not? It's not obvious. I'll let you know why in 2 seconds. So, sine x, let me do this here. X to the 2n plus 1. Okay. Why is this limit 0? Why is the limit of this one 0? Yes? Sure, you could say it's x times x times x times x times x. Sure? Done? Okay. Okay, that's one way. I think you can do that. And what's another way? Well, I mean, yeah. Another way that you have seen. It goes back to series. let me try the ratio test for this one. If the ratio test for this one gives me 0, then the series of these terms converge. So this term must go to 0.